And we'll check it is recording, it's got sound. Okay. So I'm not using any USB 3.0 devices, and hopefully that's the reason why it crashed the previous times. Alright, so let's go back to the class. What we'll do today is we'll talk about what is semantic entailment and what is syntactic entailment. How many people read that part of the notes? A little bit at least. No? Okay, a little bit. Okay. So we'll take a look at that stuff. And how many people looked up other resources online and see what other websites have to say about semantic entailment and also syntactic entailment? Not a whole lot, okay? Since we're waiting for Moodle to come in, and network connection is actually good. So, uh-oh. That is not good. Alright, so we have an issue here. Well, we have an IP address. Question is, can we resolve? Yeah, we can resolve IP addresses. So why is Moodle not responding? No, it is. Okay. All right, so we're back to the notes. Excellent. And we were talking about propositional logic. Let me zoom in. Here we go. And we were reading this particular slide here. And we talked about most of the mechanisms here. And now we are ready to talk about what is soundness and what is completeness in the context of propositional logic. Before the class ended on Monday, I kind of mentioned what it is, what those two items are. So today what we'll do is we'll take a look at the formal treatment of semantic entailment and also syntactic entailment. And then we'll also bring everything back to why is it important, how does it apply to propositional logic in the context of automated theorem proving. So this is the definition of semantic entailment. So this junk here is kind of important. I don't want to skip over it because I know if I skip over that, most people would not try to read through it. So I'm going to go through this and make sure that I can explain all of this stuff here so that everybody can understand it. So one way to define a semantic entailment is, well, first of all, we just define a whole bunch of terms, okay? So the first bunch of terms are these guys. These are phi 1, phi 2, all the way up to phi n. So we have a whole bunch of formulae, okay, that are called the phi's with a subscript number. And then we have another one which has a distinct name of psi. And all of these, okay, all of these are formulae. They are well-formed formulas. Each formula can only involve propositional variables. In other words, you look at each one, and each one becomes basically a formula that only has propositional variables without schemata. Okay? In other words, when you expand each one, it becomes like P and Q or R and stuff like that. It does not involve Greek letters once you expand them. And then we further assume that there are M variables involved, and they will be going from PM to P1 to PM. So we have a whole bunch of formulas. Okay? The phi's and the psi are formulas, and then the p's are the variables. Are we doing okay so far with this? Sort of? Okay. And then the next thing we do is we define a domain that is just a true-false, but is the mth dimension of the mth degree Cartesian product of true-false. So we just basically go, okay, 0, 1 as a set cross with 0, 1 as a set cross with 0, 1 as a set n times. Excuse me, m times. Are we doing okay so far with all of that stuff here? Okay. So if I were to just write down on the whiteboard, just as a summary of what we have at this point, we have n well-formed formulas. Okay. We have m variables involved in these formulas. Well, there's technically n plus 1 because there are n phi's, and then there's one psi at the end of that. But all of those involve only m variables. Is that okay? Yep.
Why is there a psi at the end of it?
Just so that we can differentiate between the set of the phi's versus the psi. The phi's means one particular thing. So when we get to the later points, then we'll start to see, oh, okay, so one is the starting point and the other one is the ending point. The phi's are the starting points. This is what we're given with, and the psi is what we're trying to prove. Okay. So the domain is really the Cartesian product of quote unquote all of the variables. So that's why since we have m variables, we have a Cartesian product of m true-false sets. In other words, the domain D spans the entire possible space of all the possible combinations of all the variables. Are we okay with that concept?
Kind of like a truth table?
It is a gigantic truth table, but it's not really the entire truth table. This is just the part where we explore all the possibilities, how we can combine the different values of all the different variables. Are we doing okay so far? Okay. Okay. Let's use a particular example. Okay. Something that we know about. Okay. So let's say phi 1 is defined to be P implies Q. Okay. P implies Q. Is that okay? So this is not in the notes. Make sure that you write it down on a piece of paper if you need to. Phi 2, we'll just have two phi's in this case. Phi 2 is just P by itself. Okay. Are we doing okay so far with this? And then we have psi, which is what we're trying to prove. That is just Q by itself. Are we doing okay? So in this particular case, we just so happen to have n being 2 because there are two phi's, and m is also 2 because we only have two variables. P is a variable, Q is a variable. That's supposed to be consistent with my notes here. This should be P1 and that should be P2, but I'm just going to stick with P and Q for now. Are we okay with this so far? Yep, go ahead.
So you're saying, I missed that you said P1 is P and then P2
is Q. Well, just to be consistent with my notes, because in the notes, I use P1, P2 all the way up to Pm to denote all the variables, but in this, I just use Q, P and Q to denote the variables. But there are still variables, so that part has not changed. I just changed the terminology a little bit. Does anyone want me to change everything back to just P1 and P2, or is PQ okay with you guys? Okay, all right. So let's stick with just PQ for now. So the idea is we want to define a domain. In this case, it's really easy because we only have two variables. This is representing all the values of the first variable. Let's just call it P. And this is representing all the values that the second variable can take on, which is our Q. In other words, when you look at the domain, D, it is basically spanning the entire space of every single possible value combination of the variables. Is that okay? What does it look like? There'll be tuples, right? The inside would be the tuples. So we have 0, 0 as 1, 0, 1 as 1, 1, 0 as 1, and then 1, 1 as 1. Is that making any sense? That's how we define the Cartesian product.
So you're going to use 1s and 0s every time?
Yeah.
To the m. Okay.
Yeah. So when you have three variables, then you will have it will be the Cartesian product of three true-false sets. In other words, D is really here just to span the entire space. the number of elements of D would be the number of rows in the truth table. Yep.
No, it wouldn't have to be 0 and 1, would it?
What else can it be?
So is it only 0 and 1?
Because 0 is false and 1 is true, P is a Boolean variable, so it can only take on a value of true or a value of false.
Okay.
So that's why, you know, I only have 0, 1 here,
I was
because
just
0 is
wondering.
not exactly the value 0, it means false in propositional logic.
Okay, so we wouldn't be dealing with a case where P is like 15 or something.
No, P cannot be 15 because P is a propositional
It's just a
variable,
Boolean
which is a
variable.
Boolean.
Okay.
Yep.
So when you said that they correspond to the elements in the truth table, do you mean like the powers correspond, so the M corresponds?
Okay, when we make a truth table, we try to make a one row for each possible combination of values for the independent variables. P and Q are independent. As a result, P can take on the value of false and the value of true, right?
Oh, okay. So
But Q can take on the value of false and true while P is false, and the same thing while P is true. So that's why we have all of these things.
Okay.
It's just a different way of spelling it out, because I don't like to use, okay, this way is okay, using an example to illustrate is good, but I want to kind of describe it in a much more abstract sense so that it is applicable to just about anything that we encounter. Okay, so we have D already figured out, and then we have an F here, okay? So F is a function such that when you, so it maps from D, our domain space D, to just true, false. And the way we define that is F of P1 up to Pm is really just the conjunction of all the phi's. So let's see how that is applied in this particular case. So when in this case, we have phi1 and phi2. So these two become components in the conjunction of the function f. In other words, how we define f is f of pq is just phi1 and phi2. But since we know what is phi1 and what is phi2, we just expand phi1. Phi1 is p implies q, right? That's how we define phi1. And then phi2 is just p all by itself, which is fine. There's no problem with having a function that is just a single variable. Are we doing okay so far with the definition of f as a function? It's the conjunction of all the phi's. Is that okay? And can everybody see how f is using D as the domain and has a codomain of just true, false? Yes? Okay? All right. Yep.
Is your microphone picking up? Because it's not out like it usually is.
Oh, you mean the audio part?
Yeah.
Well, we can check. I did not prop it up, but it's supposed to have an omnidirectional thing. So yes, it is picking up.
Okay.
La 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 la. Yeah, it is working. Just making sure. Okay, so that's how we define f, which is the conjunction of all the phi's. And then G is basically just psi itself. So by definition, we define G as a function. It takes on the same variables, okay? Because we only have m variables, in this case 2, and it takes on the same 2 variables. But the definition of G is really just psi itself. In this case, our psi is nothing more than just Q all by itself, which is fine, okay? And somebody may complain and say, but that's not going to work because we have 2 variables into the function. It has 2 parameters, but it's only making use of one of the 2 parameters. That's okay. There's nothing wrong with this, okay? It simply means that it ignores one of the 2 parameters, which is okay. Are we okay at this point with the definitions? What the phi's are, what the psi is, what is D, how we define F, and how we define G. The phi's are the starting points. The psi is what we want to prove, okay, as well-formed formulae. And then the domain spans over all the possible combinations of values of all the variables. That's what D is. Okay, but once we have D as a domain, then we can define the two functions. F is a conjunction of all of the phi's, and then G is nothing more than just psi all by itself. So these are just definitions. We haven't really worked on anything other than just definitions at this point. Yep.
So is it a conjunction because it's saying this is all true?
Because in a propositional logic system, if a well-formed formula exists, it means it is true. So we are basically saying, these two well-formed formulae are in the system because they are true. Is that okay? So what we want to do is to say, okay, if I look at all the phi's, do they imply psi logically? That's what we're trying to figure out. Because that is the definition of semantic entailment.
So you wouldn't put a false one in there on purpose?
No. Because what we're trying to do is to figure out, because with semantic entailment, what we're trying to do is to say, okay, in normal logic, okay, do these well-formed formulae imply this particular one under the normal logic system? That's what we're trying to figure out.
So you wouldn't throw one in as part of like proof by contradiction or something like that?
Proof by contradiction can be thrown in because we can actually prove the mechanism of proof by contradiction works,
Well, I guess-
but not in this context.
I guess you could make one of the phi's negated to start.
Oh, you can make some of these negated. So we will get to proof by contradiction next. Okay, how about that?
Okay.
So we'll get along with this particular example first, and then we'll get back to proof by contradiction and see how that works out. Okay. So at this point, are we clear on the definitions? Just how we define things. Are we doing okay? All right. So now we're getting to the part where the definition of semantic entailment is actually defined. Yes.
Actually, I do have one question.
Yeah.
Are 0 and 1 the true and false values?
0
allowed
is
in
false.
Well-formed formulas. Like, can you say P implies 0, and that's a well-formed formula that P implies something is false? Would that be considered well-formed?
Okay.
formula?
P implies, okay, let's go back to the definition of well-formed formula, how we define alpha, and then we see, okay, let's check whether it is a well-formed formula or not, okay? So P implies 0. So the question is that a well-formed formula? So now you look at all these three things and tell me what they are. What is P? P is an element of alpha because it's a variable, right? What is 0? 0 is also an element. Okay, you just have to turn your head sideways to look at the element of, okay? It's also an element of A,
Alright.
of alpha, right? Because it is a constant.
I wasn't sure.
Okay? What about this guy here? This is a connective, which means it belongs to the omega. But to be more specific, it belongs to omega 2 because it has 2 parameters. So this guy belongs to omega 2. So now we have something from the set alpha with a connective that takes 2 parameters, and then another thing from something from the alpha set. So it is well formed. It is a WFF. It's a well formed formula.
I just was a little bit unsure about the whole constants thing. Thanks for clarifying.
No. That's perfectly okay. It doesn't mean that this is always true. Okay. It doesn't say anything about its truth value. It simply means it is syntactically correct. It is an entity that we might be interested in. Because anything that is syntactically incorrect, we're not even interested. Okay? Is that okay? That was a good question, because it helps to connect with the things that we have talked about in the previous class. Okay, so.
But there's no schemata.
Huh? In this case, there are no schemata because P is not a schemata. A schemata would be one that is a Greek letter, like rho, phi, psi. Those would be schematas. Because a schemata represents not a particular value. You don't just when you see a schemata, you don't think of just, oh, this thing is either true or false. You basically say, oh, this schemata by itself can be any well-formed formula. That's why we have the schemata as different names.
Oh, okay. So would that mean that these what is it, the five, those are like schematas themselves?
They are schematas themselves, but when you expand each one, it cannot contain further schemata.
You can't nest them.
Right, exactly. Okay, so good questions. Any other questions? No other questions? All right. So now we are actually getting to the actual definition of what is semantic entailment. The symbol of semantic entailment is this one here. It looks like the one that we use in inference, okay, infer, but it's different, okay, because it has got 2 bars instead of 1 bar. So semantic entailment means, okay, so when I claim this thing here, which basically means the set of the well-formed formulae, phi 1 up to phi n, semantically entails the well-formed formula psi. When I claim that, it means the following thing has to be true. What do we mean by the following thing? It basically means for all elements in D, okay, because each element in D is an M tuple, because we have got M 0 1s, it's the Cartesian product of the 0 1s, but M times. So each element is basically an M tuple, and within the M tuple, it has got M values. So we have got a combination of 0s and 1s, but M of them as a tuple. So what do we do with that element? The way we use these elements, the 0s and 1s, which are the Q's here, is we have to we pass all of those as parameters to function f, and function f is the conjunction of all the phi's, and we want to make sure that that particular value implies G of exactly the same parameters. So you can see how we use the same parameters here, Q1 all the way up to Qm, and Q1 all the way up to Qm over here, but the functions are different. We want f of these things to imply G of the same things. If this holds true for all elements in D, then we can claim that phi 1 to phi n as a set semantically entails phi, and they are all well-formed formulae. Are we doing okay so far with this, just in terms of concept? So the next question now is to say, okay, when we look at our example, does f implies G for all possible cases? So we'll go ahead and take a look in our particular example here. So I'm just going to simplify, instead of saying f pq, I'm just saying f and then G over here. All right, so we take a look at 0, 0, and the way we define f here, okay? So it has P implies Q and P. First of all, does 0 imply 0? Yes. What about P itself? P itself is false. So that means f of 0, 0 is
False.
false. No, it's false because it is true and false. Okay, let's go over that one more time. P is 0, Q is 0. We are working with the first row of the truth table. Okay? So when we go back to the definition of what is f, the first component is P implies Q. Does 0 imply 0? 0 implies whatever. Okay, so 0 implies 0 is true. So the first part of the conjunction is true. What about the second part of the conjunction? What about P all by itself? We're talking about the first row here. P is false. So that means the conjunction itself is false. So after you apply 0, 0 to f, the end result is false. And we can quite easily come to the same conclusion. The next one is false as well, because it has a P in the conjunction, and P is false in the second row as well. So we know on the second row, the result of f is false as well. Are we doing okay with this? Okay, what about this one here? P is 1, Q is 0. Well, if P is 1, Q is 0, 1 or true implies false is false already. So that means the conjunction has to be false. All right, that's false too. What about the last one? P is true, Q is true. True implies true is true. P by itself is true as well. True and true is true. So we have a true finally as the last row. So now we look at G, okay, and go, okay, what about G of 0, 0? Well, G is easy because G of some PQ is really just Q all by itself. We just look at the second parameter. So we just copy Q over here on the column of G. So we have 0, 1, 0, 1 here. Okay? But do I need these two columns? Do I need the column for F and the column of G to match exactly? Is that what the definition call for? No, it's calling for implication. So we have to look at each row and see if the implication is true. We are not looking for an exact match. We just need the F column to imply the G column. Okay, let's take a look. Does false imply false?
Yes.
False implies whatever, right? Okay, so check. Does false implies true? I just said false implies anything, so that row checks out as well. Does false implies false, which is the same thing as the first one? It does. Okay, so this implication works out too. Does true imply true? Does true imply true? Yes. So it works out for every single row, which means I can now claim that the set that contains P implies Q as one element, P as another element, that set of well-formed formulae symmetrically entails psi, and psi is just Q all by itself. Is that okay? Yep.
Is that why the function f and g, the domain, or maps the domain to 1 and 0, because that's what
Yes.
we're going to use?
Yep, because the result of F is either true or false. The result of G is only true or false. Yep. Okay, are we doing okay so far? So with this example, I think it's a little bit easier to understand. Without the example, I guess it's a little bit abstract. Yep.
So how would you say that when you say, or how would you write that down that it's true?
You basically just say that because for each, you use exactly this thing here. And you just say that basically for all elements in the domain, D, F of that particular element in the domain implies Q of that element of the domain. But it has to hold true for every single element in D. If you have one single element where this implication does not work, then semantic entailment is not true for that particular setup. Okay. So remember the three questions: the how, the what, and the why. Okay, this is the what. Excuse me. This is the how, which is all the details, all the symbols, all the definitions, and stuff like that. But what are we trying to express here?
We're trying to prove stuff.
Well, sort of. Okay, what we are trying to illustrate here is the meaning of semantic entailment. Okay, and why do we need this? Because we need a sanity check. Before you program something in mechanically so that you can use a computer to prove theorems, you have to make sure that the rules that you put into the system to prove theorems is consistent with the actual logic that we use in mathematics. So semantic entailment is basically expressing what is correct. That's what it's saying, okay? What is considered correct. Is that okay? All right. Well, we can come back and talk about this a little bit more when you guys have questions. So the next thing we want to do, okay, this whole thing, the rest of this is really a description of the process to do what I just did on the whiteboard. Okay, so the whiteboard actually has an instance of applying what is described in the notes.
So we can basically sum up that big chunk of stuff with that one symbol.
Which symbol?
The slash.
You mean this symbol here?
Yeah.
Yeah, it's a very simple. When we see this, when we claim this is true, it means this is true.
Yeah.
Okay. All right. So now, remember I said something about proof by contradiction? So let's go ahead and work out proof by contradiction and see if we can come up with the same kind of proof. Okay. Does anyone want me to turn on the lights for the whiteboard because it's kind of dark? No, it's okay. Yes. Okay. So let me turn on the light just for the whiteboard. There we go. At home, I have a SmartThings hub, so I can just use my cell phone and turn on and turn off any light that is connected to the SmartThings hub, including the garage door too, actually. Okay, so we just have to change a few things here, okay? Because proof by contradiction is actually kind of similar to what we just did, except things are flipped. Okay, so proof by contradiction still has this thing here. I guess I should not have erased that. We still have the implication. We still have the premise of P implies Q. But this time, instead of providing P as a given, we are now providing not Q as a given. Okay, so we are basically saying P implies Q, but we also know that Q is not true. Okay, so because of proof by contradiction basically relies on the conclusion that if Q is not true, then P cannot be true either. So we are given P implies Q and not Q, and we are trying to prove that these two combined imply not P. That's what we're trying to prove. So the way we define F is going to be just a combination of these things. So the first one is P implies Q just like before, and then the second item is the negation of Q, which is fine because it's just whatever psi 2 is. I mean phi 2. And then psi itself is also changed because it is the negation of P. So we change that from what we had before, which is Q. So this time it is the negation of P, just like that. Does everybody understand how I plugged in these things? All I did was actually just to change phi 2 and psi compared to the previous example. But I want to see if P implies Q as one element, not Q as another element as a set, does that semantically entail not P? Okay, that's what I want to see. So I want to work out the truth table again. So let's go ahead and work out the truth table. We just have to erase one part of the truth table because the format of the truth table is still the same. We still only have two independent variables. So let's figure out what if P is 0, Q is 0. What is the value of F? Okay. P implies Q is true because 0 implies false is true. And Q is false to begin with, so not Q, which is not false, is true. Yep, go ahead.
Isn't the first one just the same as 40001 because we didn't change anything?
What?
No,
we changed one thing. We changed one thing that is really important.
No, but the first, the entire F column should be the same.
No. Because F is not the same anymore.
Oh,
because F has phi 2 as a component, and we changed phi 2.
Oh, okay, sorry.
So that's why it's not the same.
What F was.
Right. I think you just forgot that we have phi 2 as a component of F. Because even though we kept P implies Q as phi 1, phi 2 has changed.
I thought it was just phi 1 and phi 2.
No biggie. It's okay, no biggie. So we know that for this row it is a 1, okay? What about the next row? 0 implies 1 is true, right? Yeah, go ahead.
Are you doing the domain right now?
The domain remains the same because we only have two variables just like last time.
Is that what you're testing right now?
I'm testing for each row. What would be f of 0, 0? The answer is 1.
Because I noticed that the Cartesian product is that truth table you're doing.
Yes.
Okay.
Because earlier I mentioned the cardinality of the domain should be the number of rows in the truth table. Because we are saying for each element in D doing blah, 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 right?
Mm-hmm.
So that means, the number of rows in the truth table should be the same as the number of elements in D, or the cardinality of D. Okay, what about the next one? 0 implies 1 is true. Unfortunately, not true is false. So we have a 0 here. Okay. The next row here is true implies false. That's false to begin with. So that's going to be a 0 here. The last one we have true implies true, which is true, but not Q is false. So we have a 0 down here as well. So the truth table is not the same as before, okay? It has changed. G is really simple, not as simple as last time because we have a negation on P instead of just P itself, but it's still pretty easy. So we just look at P is a 0, the negation of that is a 1, so we have 1, 1, 0, 0 here. So now the question is, does on each row, does the value of F imply the value of G? That's the question. So we ask these questions. Is that true?
Yes.
Yes. How about this one? Works out. This one works out. This one works out. So that means the set of these two well-formed formulae, P implies Q, and also not Q as an element in the set, these two combined semantically entails not P. Are we doing okay so far? All right.
So is this kind of like a reduction?
Is it what?
Is this like a reduction?
No, it's kind of a proof, in a way, but we are, instead of using steps to prove, we are using a truth table to prove theorems. So we are actually proving a theorem, except we are using a truth table to do that. Okay. All right. So now that we are done with this one, I'm not going to go through the example here. We're going to talk about what is syntactic entailment. This is a really short one, because syntactic entailment simply means under the assumption of a particular propositional logic system. Now remind me again, when we deal with a propositional logic system, which is starts with a funny looking L, what are the tuples inside a propositional logic system? We have A to define the alphabet, right?
Mm-hmm.
The constants, the variables, the schemata, okay? And then we have the omega as a whole to define the connectives, right? And then we have iota to define everything that is true by definition. And then we have one last one, which is zeta to describe all the transformations. Is that okay? So syntactic entailment is simply saying, if we start with phi 1 all the way up to phi n, okay, and the psi just like last time, okay, so we have some well-formed formulae that we are considering. The question is, can we go from the phi's and eventually end up as in the psi? Do these transformation rules work so that we can start with phi 1 to phi n and eventually get to psi? If it does, then we say phi 1 up to phi n as a set syntactically entails psi as another well-formed formula. Is that okay so far? Okay. So this means if I mess up zeta and use a syntactical rule that does not make any sense, then something can syntactically entails, but it is not semantically entailing. Is that making any sense?
So is this more important for figuring out if that's not the case? So you go, okay, like this is not, this does not syntactically entail because something in the data is off.
Okay, think of it this way. Semantic entailment is asking, logically speaking, okay, if you look at the meaning of the symbols, conjunction, disjunction, and stuff like that, can we prove that psi 1 up to psi n implies phi? That's what it's asking, okay? And we can use a truth table to prove that because it's Boolean algebra, okay? So truth tables are very useful for proving stuff in Boolean algebra because otherwise it would be a lot more difficult. So that's semantic entailment. It's basically just saying, okay, if we just use normal math and normal logic, can we prove this? Is that okay? That's semantic entailment. Syntactic entailment is basically saying, if I specify a system of transformations which can be done mechanically using a computer, can we mechanically, using syntactic manipulation, can we start with phi 1 to phi n and end up with psi? That's the question of syntactic entailment. Is that okay? One is done by people, okay? We will do it using the semantic entailment way because we prove by various techniques. But if you want the computer to do theorem proving, you have to turn it into something that is mechanical, right? And the mechanical aspect is captured by the propositional logic system, which is basically this thing here. Okay, so we syntactically, mechanically define what the symbols can be, what can be used to connect those symbols, what is true to start off with, and how we can do transformations. So if I specify something, I'll go to you a little bit later, okay? So if I make a mistake in zeta, okay, let's just say I make a mistake. So I can actually have a derivation or a syntactic transformation that does not match actual logic. So I can say, okay, these things semantically or syntactically entails that, but semantically they do not entail. Then we have a problem because now my mechanical system is no longer matching the meaning system that we use for proving theorems. Yep, go ahead.
Wouldn't it be more correct to say that zeta matches is how mathematics is actually done? Because you do like I know zeta has things like A and B implies
Okay.
A.
Okay, let's back up a little bit. Zeta is a set of transformations, or we call inference, right?
Yeah.
It doesn't mean that zeta has to match reality.
Yeah. No, I mean in general, one of the basic sets that people use, transformation rules, includes various things like A and B turnstile A.
Yes.
This is, I just used that as an example because I did take a propositional logic course in the past, but it wouldn't zeta match the
it
how
should
people
match.
think and
It
how
should.
people do.
Yes.
Whereas syntactic entailment is more why wouldn't syntactic entailment be something you could more easily do with a computer? Because that's just computation. You can just go through all of the 2 to the n possibilities.
Okay, let me draw another picture that's a little bit. Can I erase this part? Okay. I was told by some students that certain math professors, and they did not name the math professor, like to scribble a lot on the whiteboard, and before asking, whether students have already copied everything done, that person would start to erase and then start to write more stuff on the whiteboard. So the entire class, just spend the entire time trying to catch up with the professor, on the material on the whiteboard.
Sounds like
I try my best not to do that.
Thank you.
But sometimes it might still happen, and that's why I asked. Okay, so look at this one here. Okay, that's a dead pen. We have a lot of those here. The green one is hard to erase, so I would rather not use it. I know computers don't really look like this anymore, but I'm going to use that to represent a computer. Okay. So, one is used by people. Okay. When it's used by people, it is semantic. Okay. When it's used by computer, it is syntactic. Okay. It's just like when you deal with words. Okay. When you type an English paper using a word processor, you are dealing with the semantics of those words. You're connecting the ideas, you know what you're trying to express, but the computer, even with grammar checking, can only deal with the syntactic part of it. Okay, are you matching the tenses? Are you matching the plurality of stuff? Okay, so it's dealing with the syntactic aspect of something, but you are dealing with the semantic aspect of something. Are we doing okay so far, differentiating the term semantic versus syntactic?
But isn't semantic just the truth table thing, where you have zeros and ones?
Yes,
and
but that's based on how we define the operators. But zeta does not have to match that.
Yeah, I didn't say that I had to match that. I said, if we know that, if we have like a set of premises that we know are true, then wouldn't semantic, semantic inference be easier to compute? Because you can just go and look at all the you can just go look through a formula, look at all the variables, and make a truth table. The computer can make a truth table easily because because that's what computers are good at, and computers can compute pretty easily. So, whereas in real life, I'm pretty sure that if you're doing a mathematical proof, you're not going to be checking a bunch of truth tables. You're going to be like, okay, A implies B and B implies C, so therefore A implies C. You're doing it more syntactically than semantically. Because
the way we do things, I don't know exactly. Okay? Because we don't know what is going on up here. Does that make any sense? When you prove a theorem in linear algebra, okay, you are applying what you understand semantically about the theorems and whatnot.
How would you implement the syntactic proof checker? Like, supposing that you had theta, and you have something that has a set of rules that are true. Maybe it's not complete, but it has a set of rules that are true. How would you go about implementing that in a computer? Because with the semantic, you can just do a truth table, but with the syntactic, it seems like it would be harder and more computationally intensive to put that in. Whereas the semantic it is going to be computationally intensive, but I don't see how you can really go past a constant or maybe past a polynomial difference when you switch from semantics to syntactic.
Well, the answer to that question is, over time, computation power, becomes more and it becomes more and more, because of Moore's law, right? So we have more and more powerful computers. How many people have used the feature on the TI calculator to solve an integration symbolically or differentiation? Okay, and that technology was not in existence when I took calculus. When I took calculus, the internet was not even there. Okay, I could not even just log into wolfram.com and solve the equations. So I had to solve all of those equations by hand because the calculator can calculate, right? It can numerically do the integration by approximation, but it cannot symbolically perform the integrations. So so that's the point, okay? Because as time goes on, I prove theorems, I do all the derivations, not mechanically, I just do it semantically because I understand what I'm dealing with, okay? But the computer, the calculator, is doing everything, guess what? Syntactically. Because that's the only thing it understands. The calculator doesn't understand what is integration, what is infinite, and all that stuff. The calculator treats everything as a symbol, and there are rules to help it to transform from one to another, one form to another form.
I would say the whole reason for computers is they do way harder proofs than we can.
It can do a lot of things a lot faster than we can,
Yeah.
especially when it is purely mechanical stuff. Okay, so I would challenge those of you who have taken CISP 310 to convert a C program into assembly code. And then you run the compiler and see who's faster. Now we do things by semantics, right? We look at the code, the meaning of the code. Oh, this is a loop, which means it's doing things over and over again. This is a variable, this is an integer, blah, 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 blah. So we do the translation by semantics, by meanings, okay? Because everything has meaning in our head. The computer doesn't understand it, right? The computer look at the for loop and go like, okay, I know how to syntactically or mechanically translate this into the equivalent instruction sequence or structure, but it doesn't really understand what a loop is. Okay, it just says, I see this, I transform that. I see this, I transform that. Is that making any sense? But who's faster?
Assembly.
The compiler is faster, right? The compiler is much faster than we are because once we turn something into syntactical rules, in syntactic transformations, the computer can apply that stuff a lot faster than we can. fine. Some people have like, okay, this is just my philosophy, okay, so you can ignore this part. It won't be in any exams. Some people have a thinking box like this, okay? Some people have a bigger thinking box. But some people, especially people with ADD, have strange thinking boxes that are of very strange shapes. So, ADD people have a thinking box that it has a shape like this. In terms of volume, it may not be any bigger, but the shape is different. Which means they can come up with certain ideas faster because they are not a normal thinking box shape. So if I can reprogram myself, I would change my thinking box. I would find a way to expand the thinking box. I don't want more memory because the computer can do that. But anyway, that's just it's just sparked that kind of discussion. So getting back to this, okay. So do we have a good understanding now about the highest level of concept, the why of why we are talking about these entailment stuff? Semantic entailment is what we do. Syntactic entailment is what the machines do. Soundness is basically saying in this direction. No, the other way. So soundness is going from the syntactic to the semantic direction. So it goes from here to here. If your syntactical rules are sound, it means that if the machine can prove something, so should you be able to do. You should be able to do that as well. That's soundness. Completeness is the opposite direction. If you can do something, so should the machine be. The machine should be able to do the same. And we would like both. Okay? In any logic system, we would like to have both so that the computer can eventually replace all of us.
That's exactly what.
And of course, it will be running on top of some Microsoft operating system. Yep.
Is there a term for both, like bijective?
I do not think so. You can probably look it up. So you can just look up both semantic and syntactic entailment, and look it up.
Just go over the article. There you go.
Yep. That may not be in the context of intelligent utterance. I don't think that's applicable to us.
A lot of it is philosophy stuff.
Yes, it is.
So-
But it also has applications in computer science because we are getting to the point where we can actually do at least a part of this.
So
was
an example of something that would be complete would be like a program that takes payment that can also make change.
Not quite applicable in this context. In this context, we are basically just saying, okay, if you have a way to do something, the computer should do exactly the same. So let's just take linear algebra as an example. Okay, so if you have a system that can prove theorems in linear algebra, okay, which means you have somehow derived all of these things, but specifically for linear algebra. Okay, so let's say you have a system like that. You have all the transformation rules, you have the iota, and everything that goes with it. So we want that system to have this relationship with what you can do as a person. Because, okay, so let's see what happens when this equivalency is not there. Okay, what if there's no equivalency? So that means sometimes, there's a theorem that is actually true. You can prove it as a person, but a computer would not be able to do it. That can happen without the equivalency. It can also happen in the opposite direction. The theorem, the computer can prove a theorem that is not true. The computer comes to the conclusion of something is syntactically entailing, but then when you try to prove it, then you say, no, that's not true. This theorem is not true. So we don't want that to happen either. So that's why we want the equivalency to basically say, if you can prove it to be true, the computer should be able to do the same. If the computer can prove it to be true, so you should be able to do the same.
And the main reason that the computer wouldn't be able to prove it would be because it has incomplete information.
Because because one of these things is incorrect, or because the propositional logic itself is not sufficient to process what you need to prove, which does happen. Because propositional logic has limitations. And particularly, it has no concept of quantification. It has no concept of for each and for all, that sort of thing. So it can only do certain basic logic manipulation, but not everything that we need to do in mathematics. But it's a good starting point. Is that okay or not? Kinda? Okay. It might take you some time to kind of let these things sink in a little bit, but as you think about these things, you make sure that you don't focus on just the how, which is the low-level stuff, but also the what and also the why. Is that okay or not? Okay. All right. So let's move on to the next one, because at this point, I cannot give you any homework assignments, because propositional logic, even though I can technically give you homework assignments, is not going to be very useful, okay, because it doesn't really connect to what we want computers to do. So the next thing we want to do is to talk about normal forms, okay, which is a really kind of short slide, because a normal form is, okay, let's take a look at this description here. A normal form in logic is a well-formed formula, okay, so it is a well-formed formula that conforms to a certain format with restrictions of how certain operators can be used in the structure. Okay, so it doesn't really say much, does it? A conjunctive normal form, a CNF in this class, is one that is a conjunction of disjunctions. If you are taking CISP 310 in the same semester, and I can see a few people doing that, this is the opposite of what we do in that class. Okay, just a clear disclaimer in the beginning, okay? Okay, so let's take a look at what is a conjunctive normal form, and we'll finish this part here. It is it's a conjunction, okay? So at the top level, it is a conjunction, and the components of the conjunction are disjunctions by themselves. And inside each disjunction, you can only use either a variable or the negation of a variable. You can have any combination of variables and negated variables, but nothing else inside the disjunction. Are we doing okay so far with that concept? Okay, so let's take a look at this part here. Is this in CNF, in conjunctive normal form? Is the overall thing a conjunction?
Yes.
In other words, is conjunction the very last thing that you're doing?
Yeah.
Okay? If you look at each component of the conjunction, is it a disjunction of some kind that only involves variables? Let's just say A, B, C are variables, or the negation of variables. Okay, some people can complain and say that, hey, A is not a disjunction. What is going to happen here? Well, if you really want it to be a disjunction, you can say A or 0. That would make it a disjunction. And then some people would say, yeah, that would make it a disjunction already. But then some people would say, but A or 0, 0 is a constant. It is not in the form of a variable or the negation of a variable. Can we fix that?
Not one.
Well, you cannot just negate that. So
P
we'll.
and not P.
But then you have an and inside the or, which is not allowed.
Could be or not A.
Hmm?
Or not A.
That's true though.
But that would become true. So you have to allow constants in that case. But we will basically just say that an individual variable is already considered okay. Okay. What about this one here? Is that in CNF?
Yep.
What is the last operation of this entire thing? The last thing is an or, which makes it it is not a CNF. Because in the CNF or conjunctive normal form, the last operation is a conjunction.
It's almost DNF.
It is almost DNF, but it's not DNF either, because you have a negation that is not applied to a single variable.
Yeah, so
You have a negation that applies to the conjunction of variables, which makes it not even, it's not DNF, it's not CNF either. Okay, are there any questions about what is a CNF? What is a conjunctive normal form? Yes? No? Sort of? Okay, so let's go ahead and see how we can convert something into a CNF. So we will start with something that looks like this. The equal to is really the same thing as equivalent to. In other words, when I use equal to in this context, it really is a bidirectional arrow. Okay? It is equivalent to. Okay? So P is equivalent to Q, and then this whole thing is equivalent to R. Okay, that's what we're stating here. So the question is, how do we convert this into CNF, conjunctive normal form? Okay? So the very first thing we need to do is to not use equivalent to and change everything to use disjunction, conjunction, and negation. So this whole thing becomes this thing here because this is the first part of this, okay, because it's going in both directions. When we say P and Q are equivalent, we are basically saying P implies Q and Q implies A. So the first part, the highlighted part here, is saying P implies Q. This part is saying Q implies P. Okay, and then we still have one equal to on the outside, but we can now convert that one, and you can see. Okay, where's my scroll bar? Okay, I have to find my scroll bar. It's probably at the bottom here. There we go. Oh, if you're not in CISP 310, don't complain, okay? Because those guys have to deal with something far worse than this. Wouldn't you agree? There was one student that I met in the hallway yesterday, and the student said, I have seen the homework assignment in CISP 310. I don't think I'm going to take that class. But it's workable. It's just that people have to put in the effort to get it done. I mean, you got it done. Yep.
I wonder if you could go quickly over what makes it CNF.
Okay, absolutely. So because all these terms are fairly standardized, over all the definitions. So if I'm not explaining something really well, one thing we can do is to go outside of my notes. Okay, so we can look up CNF. And in Boolean logic, okay, this is one source. Wikipedia is okay for the most part when it comes to math and computer science. So a conjunctive normal form looks like this. Okay, all of these are CNFs. Okay, so let's take a look at why we call all of these CNFs. The last operation is a conjunction that makes it a CNF. In this case, the last operation is a bigger conjunction that makes it a CNF. Now this one is a CNF because even though it only has a disjunction, but you can look at this entire disjunction and then say, you can always end with 1, right? Anything end 1 is whatever you start off with. So it's easy to turn A or B into CNF. So that's why we consider A or B as a CNF. A and B by itself is quite obvious it is CNF because A itself is a CNF, B itself is a CNF, and when you have conjunctions of CNFs, the whole thing becomes a CNF. Are we okay with that idea? Okay, there's another way to look at this.
Is this because of the way that we do, we define the function?
The reason why we like CNF is because it allows very easy mechanical theorem proving. So it ties into what we talked about earlier, syntactic entailment. So this makes a very simple mechanism for proving theorems. Instead of using all those like 20-something transformation rules, we end up with only like 2. Yep.
You can also use this like if you're say designing a circuit to light up only if certain things are true. You can use this to kind of figure out how you're going to structure your logic gates.
Correct. Yeah. Well, but that's assuming that you have some sort of restriction on the structure of the logic gates. Then it becomes useful. Okay, so with a CNF, what it means is you have an overall conjunction of stuff. Okay, so inside the conjunction, everything under that is a disjunction. Okay, so you have a bunch of little disjunctions, and they all merge by the overall conjunction. And then inside each disjunction, you can have either variables, okay, or the negation of a variable, but nothing else, okay? So you can have variables or the negation of variables, but not anything else. So this overall structure means that this entire thing is a Cnf. So that's one way to look at this.
And it can be multiple ands.
Yes. So this and here is applied to all the sub-expressions that are ORs.
Oh, okay.
Yep. So this is one way to look at it. There's another way to look at it as well. The other way to look at this is to define a Cnf recursively. Okay. So you can say a variable by itself is a Cnf. So if you have p, q, r, as variables in alpha, p by itself is a Cnf, q by itself is a Cnf, r by itself is a Cnf. Are we okay with that? Okay. So now we can say the negation of a variable is a Cnf. So not p is a Cnf, not q is a Cnf, not r is a Cnf. Is that okay? Okay. So the next one would now be the disjunction of these two things is a Cnf. I should say a disjunction. So any disjunction that only consists of variables and the negation of variables, that disjunction is a Cnf. Even though it has no conjunction, it is still considered in Cnf. Because you can always just say that the entire thing and 1 at the very end to turn it into a Cnf. Is that okay? Examples. P is a Cnf, not Q is a Cnf, P or Q or R is a Cnf. Is that okay? So the next one is the one that is more recursive. This is sort of recursive, but it only has one level. But the next one is kind of more recursive. Now we say, a conjunction of Cnf is a Cnf. So let's see how that can change the whole thing, because the last one is the one that makes it very expandable. Because now that we have all of these things as individual Cnfs, now we can say P and not Q, and the whole thing, P or Q or R, it is a Cnf. Is that okay? Because when you look at this whole thing, the final operations are conjunctions, but when you look at the components of the conjunction, each one only involves the disjunction of individual variables or the negation of individual variables. So it still fits that requirement. Is that okay? So depending on how you like to look at things visually or by rules, these are the two ways to understand what a Cnf is. A conjunctive normal form. Are we doing okay so far with this? Okay. In the slide here, okay, elsewhere, they talk about conversion into Cnf. I cover that as well in my own notes, okay, because I give you guys a bunch of rules that you can apply to convert something into Cnf. So if you just read through this part here, it gives you the basic rules to turn something that is not in Cnf into Cnf. So before the end of today's lecture, which we have about 5 minutes or so, I just want to kind of take a step back, okay? This stuff here, these are the hows, okay? So we want to say, okay, but what are we talking about? What are we talking about with this stuff here? Well, we are talking about Cnf, conjunctive normal form. But then the most important question is, why are we talking about this? Cnf is interesting. I'm going to give you a fast forward to the slide where it is actually applied, because Cnf lends itself to resolution. Now, resolution is a very simple rule. Okay, this is one of the rules. This is pretty much the only rule that you need, other than being commutative and stuff like that. But this is the only really useful rule in Zeta when you deal with resolution. And all it says is if you have one WFF, one well-formed formula, that is phi or psi, you have another WFF that is the negation of psi, which is the negation of these two, and then or rho, then you can come to the conclusion that phi or rho. You can derive that. Okay. So now the question is, well, does it actually work? Okay. So we can prove that this works in two different ways. The first way that we prove, okay, this is a perfect example of syntactic entailment, which is just by definition as a transformation rule, and semantic entailment, which is proved by Boolean algebra, the way we understand the operators. So I'm not going to go through the details here because you can read it on your own, and we're running out of time today. But I can just show you the end result of this derivation. The end result of this derivation is true, which basically means this statement is true, regardless of what you plug in as phi, psi, and rho. That's semantic entailment because I just prove it as a human using the meanings of the operators. This part here is syntactic entailment because I am just putting this rule into zeta. Okay, this is a quick reuse of concepts that we have talked about earlier. But this is really good. This is really useful because every time you come up with something else, this is the result of the transformation. How does that look like? How does that compare to the things that we start off with? Is it more complicated or is it less complicated? It is less complicated. In other words, as we apply these rules, repeatedly, we come up with more and more terms. Yes, we do end up with more and more terms, but each term that we come up with is no more complicated than the terms that we started off with. Which means, eventually, you will run out of ways to do transformation. You will have to stop. The program has a place to stop and say, I can do no more transformations. Which is great, because that means the algorithm will terminate. It might take a little bit of time, but it will terminate. When it terminates, there are two conditions to terminate. One way to terminate is you have a zero in the entire thing. Because think of it this way, what if this row here is the negation of phi? Then you end up with phi or, oops, that wouldn't work, would it? Nope, I take it back. Okay, so think of this scenario. Think of the first one having just psi all by itself, and then the second one having just the negation of psi by itself. The resolution rule says it was to work, except they will annihilate each other, which means the end result becomes just false. But because false is now in the system, then you have a contradiction, then you can stop. So the process of resolution is really great for automated theorem proving because there is a place where you can stop. Either you run out of things to transform because you have already transformed everything that is possible that is transformable, or you come to the conclusion that there's a contradiction, which is actually what we want. Because resolution is the mechanism that we use to prove by contradiction, but mechanically. So now we have a very mechanical way to do theorem proving using proof by contradiction. And the algorithm is guaranteed to stop at a certain point. So that is the overall why of why we care about CNF. Because if you express everything in your logic system as CNF, then we can apply resolution. But when you can apply resolution, then you can use proof by contradiction. And as a whole, then you have a way to mechanically prove theorems that is predictable. Okay, the algorithm has to stop. Whereas the other way doesn't have to stop because you can keep deriving more and more complicated well-formed formula that is useless, that makes no sense, but it doesn't stop. But this way, it has to stop, okay? Because with every single step, you are reducing the complexity of the expressions. So we'll get to this part next Monday because we are running out of time today. But I do want you guys to read everything at least up to resolution. If you can, if you have time and you want to, read, well, I guess resolution will be the last one. because the resolution one also mentions something about proof by resolution, proof by contradiction, and using resolution as a mechanism. So read up to and including resolution, and then next week we'll probably have a practice exam, which doesn't count to your grade, but it just gives you an idea of what the exam is going to have. Right.